Here's another example of a word problem we can solve by representing it as a system of equations. We'll actually do two different versions of this question. Here's the idea. We have a coffee shop that receives shipments of coffee beans and blends them together. So there are two types of beans we receive in shipments, Kona beans and Arabian beans. And then we resell them as blends. Foggy Morning blend, which is made of half Kona beans and half Arabian beans. So for example, to sell a 2-pound bag of Foggy Morning blend, we would use 1 pound of Kona beans and 1 pound of Arabian beans. And then Market blend, which is a different mixture, 1/3 Kona beans and 2/3 Arabian beans. So let's say we receive a shipment of 200 pounds of Kona beans and 250 pounds of Arabian beans. We want to mix these together to get our blends, Foggy Morning and Market. How many pounds of each blend should we make if we want to use up all of the beans and not have any left over? Well, the unknowns in this question are how many types of each blend to make. So those will be our variables. X will represent how many pounds of Foggy Morning we blend. Y will represent how many pounds of Market we blend. Now, the total number of beans we use, the total number of Kona beans, has to add up to the 200 pounds we received in the shipment. So if X is how many pounds of Foggy Morning we blend, half of that was Kona beans. If Y is how many pounds of Market we blend, 1/3 of that is Kona beans. So when we add together how many Kona beans we used in Foggy Morning and how many Kona beans we used in Market, the total should be 200 pounds of Kona beans. Similarly, we need the total amount of Arabian beans we use to add up to 250 pounds. So 1/2 of the Foggy Morning blend plus 2/3 of the Market blend are Arabian beans, and that total should equal 250. Now we have a system of equations we can solve for x and y. And there are various approaches. For this example, let's set it up as an augmented matrix so that we can apply Gauss-Jordan elimination. If we do that, for example, with the calculator, we can reduce it to this matrix, and from this we can read off the values. The first row is telling us x is 300, the second row is telling us y is 150. And the real-world meaning of those values is that we should produce 300 pounds of Foggy Morning blend, because that's what x means, and 150 pounds of Market blend, since that is what y represents. So again, you have to compute the actual Gauss-Jordan elimination somehow. You can do that by hand or using technology. Now, let's look at another version of this question. Same setup, same kinds of beans, same kinds of blends. But this time, we don't know from week to week how many pounds of each type of bean we will receive in our shipments. So what we would like to do is come up with a way of doing this question, of answering it, so that we can plug in later the amount we receive in the shipment without having to solve the entire system of equations every single time. Let's see how that might work. We will use symbols to represent how much we receive in the shipment. So K will represent how many pounds of Kona beans we receive. A will represent how many pounds of Arabian beans we receive. And we want to set up a problem just like we did before. So this is the system of equations from the previous problem we solved, except we've changed the right sides. Instead of 200 and 250, we have K and A representing those values, since we don't yet know what they are. Now, we'd like to solve this system, and in the previous example, we solved it using Gauss-Jordan elimination, but we're not going to be able to do that here on a calculator because you cannot enter these unknown values, K and A, and still perform Gauss-Jordan elimination the way we have in the past. However, we can still use the matrix equation approach. Let's see how that might work. Let's start by writing the system as a matrix equation. We have a coefficient matrix, times the matrix of unknowns, x, y, equals the right side matrix, Ka. And our goal is to isolate the matrix of unknowns, x, y, so we want to multiply both sides by the inverse of the coefficient matrix. So you can find that inverse of 1/2, 1/3, 1/2, 2/3, and you'll get 4, -2, -3, 3. So multiplying on the left, we think of that as canceling the coefficient matrix. And then on the right side of the equation, we multiply by the same thing. So we multiply the inverse of the coefficient matrix times Ka. Now this we can compute. 4 times the row 4, -2 times Ka, we get 4 times K minus 2 times A. And the second row gives us -3 times K plus 3 times A. This is just regular matrix multiplication. We cannot simplify it anymore because we don't know what the values of K and A are. But at this point, we're able to write out X and Y in terms of K and A. So we've basically at this point found formulas for X and Y. That is, if we receive K pounds of Kona blend and A pounds of K pounds of Kona beans and A pounds of Arabian beans, this formula tells us how many pounds of Foggy Morning we should blend. And this formula tells us how many pounds of Market we should blend. So later on, if we find out how much of each type of bean we receive in our shipments, we'll just be able to plug those numbers into this formula to determine what we should make. And once you have a formula like this, it would be easy to code it up, for example, in a spreadsheet to get the answer very quickly once your shipments arrive. So for example, if we get 200 pounds of Kona beans and 300 pounds of Arabian beans, we just plug those numbers 200 and 300 in for K and A, and we immediately discover that we should make 200 pounds of Foggy Morning and 300 pounds of Market blend.